Hello everyone. Today we're going to talk about parallelization in Python. So there are some basic functionality already built in to the proper Python language that allows us to parallelize some tasks. There are some additional libraries which we're going to talk in later lectures that add some more capabilities, but we're going to look at some of the basic functionality. So especially if we want to do something very simple, these are all we need without having to go to additional packages. So the module that's being used within Python is called multiprocessing. And most of the time, again, we can use an alias, so I prefer to use MP. We're going to also load up pandas. And what we're going to do is we're going to first look at how many cores we have available, so how many CPUs essentially, or processing units we have available. Now the answer here is going to be different depending on the machine you're running it in, but you see here that we get the CPU count. In my case, it's 8. So there's a few. Let me actually go to the slides here. That might be easier. There we go. Okay, so there's a few types of parallel execution that are conceptually similar in other programming languages. So these are going to be useful to you even if you don't code in Python, or if you code in something like C or Rust or any other language. So we've got the synchronous parallel execution, and those two operations, at least within Python, are called map and apply. And those have a direct correspondence to things that we've seen before, especially with pandas and xarray, of how we're mapping functions or applying functions. And we'll see the difference in a little bit between those two. But essentially what they're trying to do is apply or map a function over different parts of a data set. So if we have a pandas series, we will partition the data and send each one of those to the different processors. Now, one thing that's going to happen here is that this assumes, a multiprocessing module assumes that we're running on a shared memory architecture. Shared memory is when each of the processes that we're running can access the same memory topologically. The opposite of that is the distributed memory paradigm, where essentially what we're doing is we have actual different nodes, let's say on a cluster, that will require us to send data. So we have a main thread or a main machine that will send the different partitions of the data set to different processors. Now, processor 1 won't have access to whatever was sent to processor 2, and that's why it was called distributed. So that's an aside, but right now we're just going to focus on shared memory architectures, and that's your laptop, your computer, so anything that we've been using so far. Anyway, back to the parallel execution. So what synchronous execution will do is what the name says. So each of the different processes that are running on the different partitions of the dataset will run at the same time. Whereas if we have asynchronous, we can have the processes finishing at different times, and we would get the results back before all processes finishing. With a synchronous execution, we can only see results at the time when all of them have finished. Asynchronous, each process is kind of independent, so it will send the results back, and we can see that we can access them right away. Where this makes a difference is when the parallel execution is part of a longer computation. So for example, imagine that we could use the data that are being processed by thread 1, and we're going to use them for another calculation down the line. Well, with synchronous operation, we can't do that because all threads need to finish first, and then we can access the data. With asynchronous, that's when it's independent. So if we have something a bit more complicated, then we can use the asynchronous to make it return results faster. And then we also so those operations are within the pool object There's another object that's called process that uses a slightly different model, where although we have shared memory, it kind of assumes that we have distributed memory processes. So in some cases, depending on the computation, it can be faster. So we'll cover that a little bit. So let's get some data, and I've uploaded them on Moodle. So these are some fuel economy data from the from DOE, and we're gonna read them and we're gonna take a look. Okay, so there's a number of different fields here, and it just basically tells us some miles per gallon, the type of car, different years, different engine capacity. So a lot of characteristics there that we can use. So in our hands-on exercise, what we're going to do is we're going to create a list that has the combined miles per gallon of each car multiplied by 1.2 if it's a forward-wheel drive. So what we're going to do here is we're going to write a function to be able to do that. And that's one of the things that, because we're going to be mapping or applying within the multi-threaded pool, we need to write a separate function to do this. It could be an anonymous function, but most of the time, we're just going to write something. Now, this calculation of calculating the combined MPG and then multiplying it, it can be pretty fast. So then, we won't be able to see the effects of parallelization. So what we're going to do is we're actually going to use the sleep function from the time module that essentially will make things a little bit slower, and we'll see it in action. The columns that we're going to need is comp08 and the drive. So drive tells us if it's a forward wheel drive or not. Comp08 gives us the combined MPG. And what we're going to do is we're going to use a list comprehension and the data frame iter rows, which iterates over the rows, to actually apply this function. So first thing we're going to do is we're going to import the time. And then we are going to write a function for the MPG. So again, because we're going to use iter rows, we are going to write a function that operates on every row. So let's start def MPG and then row. We're not going to add a doc string here, we don't need it, but we're going to say if row drive equals, and actually before we do that, let me do something different. Let's open up another cell here, and let's take a look at our df here. So let's take a look at, remember df iter rows, that's that's a generator object. So if we turn it into a list, remember lazy evaluation, so let's look at the first. Actually, we could do it even better. Head 1. There we go. But let's look at the different columns, and you see there's so many of them. So what we're going to do is we're going to choose to see, actually, we can probably do it this way. Oops. Comp08 and then drive. There we go. Rear wheel drive and the miles per gallon. So let's try it now. So essentially, if the row drive is gonna be front wheel drive, then we're going to return row comp08 times 1.2, else return the row comp08. Now remember that we also need to add the time sleep. So what I'm going to do is I'm going to make sure that this waits 4 seconds in total. So hold on, let's do, well, actually not 4 seconds, but let's do this one. So let's use the length actually here, and let's do that. All right, so runs. So now we're going to time result by doing a list comprehension. So remember list comprehension, we're going to call mpg row for row in df iter rows. Okay, So that should be it. Now iter rows, remember, actually it doesn't just return the row, but it returns an index. So we need to, so row is going to be a tuple. So now we're going to need to deconstruct that and just say not something that we don't need a variable for. That's what the underscore is. So we could have put I and row in df iter rows, and then we're going to time it. So let's take a look at that. And now remember, if we run it without the sleep function, it's going to be very fast. But now we're just adding some additional time. So you see now we're getting 6.27 seconds. So, and again, remember, we wanted to get at least 4-second delay on this. So that's why we added 4 divided by the number of the rows to essentially make it, to add that since MPG operates per row. Okay, so let's keep that in mind, 6.27 seconds. Now, we're going to use the pool, the multi-threaded pool. One of the issues that we're going to find is that the function that needs to be passed into the pooling needs to be on its own module. So we're going to solve that by writing the MPG function into a separate fuel.py file. And the fuel.py file is going to look like this. Okay. Now, when we use the pool map, you see here that we import the fuel. So when we import fuel, the function fuel.mpg, so in the fuel namespace, is available to us. And again, there's a reason, because it's going to use, within the pool object, we need to have the function already part of a module. So we can't just define it within the same main thread, as we would have it. So, because what's going to happen in that case, it's not going to be able to pass the function to the different threads. So we need to have it as part of a module. So we've got import fuel here, and then we create a pool under P, and we say MP, which is the multiprocessing module, .pool, and then MP CPU count. So we're going to get 8, as we saw. For you, it might be different. Then we're going to time the results by mapping the fuel MPG function, and then here, the second argument of map is the list or the sequence of data that we want to parallelize over. So here you see that we create a list of rows from the df iter rows. So let's time this one. Let's see what happens. All right. So immediately we see that we half the time. Now, one of the things that didn't allow us to have linear scaling, because we use 8 threads, so we should have expected 8 times the speed up, is that there's always some overhead, and especially in our case, we have the overhead of constructing this list, of iter rows. So actually, why don't we do this? Why don't we create this outside of the parallelization, and let's time it now and see how much of that is an effect. Okay, you see that we shaved 1 second, just because we essentially want to parallelize the application of the MPG function, not the construction of the rows. So so you see we went from 6.27 seconds down to 2 seconds with 8 threads. So again, not linear scaling because there's overhead, but imagine if we had a longer calculation, we would probably get closer to the linear scaling. So a map, again, because it's synchronous, it will block until all threads complete the job. So again, it's synchronous application. When we apply the asynchronous, and then again, let's put here rows. All right, let's try to time this. And exactly. So again, we are not using the, overhead here at all. Let me see, I think I wanted to start. Let's get out of here. Okay, there we go. Let's look at the results. Okay, so you see here it's a lazy evaluator object. So the map async, it does not actually calculate. That's why the difference in time is so significant. So let's try to do this. Actually, let's take a look at here. Pull, apply. I think join might do it. Actually, no. Oh, pull is still running. Never mind. Let's see how we can do this. List. Let's try this. And must have changed things. All right, and with this one here, they changed it with Python 3 slightly. And essentially what we have to use, because as you saw, if we run it like this, you know, we get results being as, again, let's try this. We have lazy evaluate map result. So what we're going to do is we're going to actually use the get function with that object to get something that runs in 2.41 seconds. Let's run it again because I think we were still running the previous one. 2.22. So, you know, a bit faster, not actually a bit slower. So let me do this actually. Let's do the time it, just so we're sure. And this is why you always want to use time it, because, you know, it will give you a better idea of what's going on, since it's going to take a standard, it's going to find a mean execution time and a standard deviation. So we're going to get a much better idea in terms of benchmarking. Okay, we've got 1.73 seconds. So let's try the same thing with the synchronous and the get function. Let's delete this one. Actually, let's keep it. Okay, 1.74 seconds. So actually about the same. Tighter in terms of the standard deviation, but I expect it to be a little bit faster. But again, it's a fast operation, so it's not going to make much of a difference. In any case, let's move on to Numba parallelization. And you remember Numba was able to create a just-in-time compilation. So it made our NumPy code even faster. So in this case, we're going to try an example to see if you can parallelize. So we're going to assume that we have two large arrays of latitude, longitude coordinates, and we want to find the number of times a point in the first array is within 1 kilometer of each point in the second array. So this is an expensive operation because, again, we have to loop through all the points in the first array, and then we have to examine whether it falls within, calculate the distance and with all the other points, and then figure out if it's within 1 kilometer. So let's create some random data, and we're gonna have, remember, chord 1 and chord 2. Chord 1 is the first array of points, and it has two columns, latitude, longitude. Same thing with chord 2. So you see that for chord 1, the first column we put latitudes, longitudes in the second column, and the same thing for chord 2. So let's make sure that we import the NumPy module in case we've forgotten it. And here we go. Okay, so we've created these. Now let's define two functions to calculate the distance and find the nearby points. So what we're going to do is we're going to do distance, the radius of the Earth in kilometers, and then we're going to convert from degrees to radians, sorry, of the latitude, longitude, and then from the first array and the second array, and then we're going to calculate this, the formula that calculates, let's do this here, that calculates the distance. Okay, that's the distance. We already applied JIT on it to make it faster. And then we're going to define a function that says get nearby. So it takes chord 1, chord 2, maximum distance, which we're going to be 1 kilometer. And then what it does is it creates an output of, again, the number of points for each of the array 1. And then it's going to go from, I think we can actually do range here, but let me try. Yeah, I think we can do range here. So it will take the point from chord 1, and it will calculate the distance between point 1 and all the points in chord 2, and then find the number of points that are within max distance, which is 1 kilometer in our case. But so this boolean will give zeros and ones where it's true, whereas false and true respectively, and then if we calculate the sum, we're going to find the number of points. Okay, so that's it. Actually, let me try this here. Oh, still works. So let's leave p range. All right, so now we're going to create two functions, and we're going to JIT them, just-in-time compile them. So JIT no Python get nearby, and then we're going to add the keyword parallel true for get nearby. Okay, so we got get nearby 1, get nearby 2. So let's time the two functions. So we're going to time it. So benchmark the function get nearby 1, and we got an error. Let's see what we got here. Oh, okay, yeah, that's what I thought. Let's get rid of p range. Okay, let's do this here, and let's time it again. There we go. P range was used in Python 2 as a faster version of range, but I think with Python 3 they just replaced it. So you know, we have we can just use range directly. There were some inconsistencies sometimes depending on the number version you had, so I think that's why I've left it there. But you know, thankfully now everything is consistent, so you can use range directly. Okay, so 3.57 seconds, and remember now that it's again it's an expensive calculation. So let's try it with the parallel equals true. So let's time the get nearby 2 function. Okay, that's a warning. That's fine. Shouldn't affect things. Let's see. Okay, fine. So you might not get this warning because you know JIT will use Numba will use the OpenMP. That's the OMP. What OMP stands for? Library. That's a C library that's being used. So depending on what you have installed in your system, if it's Windows, Linux, Mac, you might get this warning. You might not get this warning. So let's take a look at if it is any faster. And it actually isn't. So that's surprising. So we're getting 4.5 seconds. So I guess the Numba parallel didn't really do much in this case, which could be related to this to the library that's installed with to the OpenMP library that's installed in Mac. So what I'm going to do also is I'm going to try it out on my Linux workstation, see if I'm getting the same result. So I'd be interested in hearing if you're seeing the same result as I am here. But theoretically, the parallel true keyword should allow you to get a speed up without having to deal with the multi-threaded Python. So I think we're going to stop here. Essentially, I just wanted to cover a few of the basics of parallelization in Python, which is the multiprocessing module. It's not used as much, it's very because it's kind of relatively low level, so you can do things much faster with additional packages. The one we're gonna talk about, and it's actually been tremendously helpful to my work, is Dask. So DASK. We're gonna talk about that the week after next. But play around with these a little bit, also with Numba and the multiprocessing, and see what you get. And don't forget to hit the like button and subscribe.